We would like now to continue our second section on fluid, which is fluid statics. And in this topic we will study the stationary fluids, that is those fluids they are not moving. So one of the example of that is the fluid in a container or pond. So in that situation, the shear force, no shear force exists over there, so only the dominant force is the pressure. So in this regard, would like to explain the pressure. Pressure is nothing but the force divided by the area onto which that force is acting. So if it is my elemental area onto which the force vector is acting, make sure the force should be in the normal to the surface. So this is a normal plane, 90-degree angle, and if that force is at normal to the surface, the area divided by the force will provide you the pressure distribution. Our objective here is to determine an equation that can predict the pressure distribution in a static fluid. So in this regard, I would like to consider the fluid in a container. For example, this is my container and the fluid is maintained at atmospheric pressure in it. So to do that, I will consider a cubical element of my fluid in that container for my analysis. So that is my cubical element, and onto which I will consider that the pressure is acting from all the direction, and subsequently I will perform the analysis on that. Now consider this infinitesimal element of fluid, so onto which you see the forces are acting in the x direction, the px on the left hand side and the incremental change in px on the right hand side. Similarly, the py on the bottom surface and py plus partial p over partial y plus del y in the y direction, and make sure that the del x is the length in x direction, del z in z direction, and del y in the y direction, the dimensions of this element. Now we will go and apply the summation of forces in x direction of this element. By the way, same forces you can extrapolate for the z direction. Now summation of forces in the x direction, you can see that the px multiplied by the area onto which the px is acting. Similarly, on the right hand side, px plus partial p over partial x into del x, the change and total pressure multiplied by the area onto the surface at which that is acting. And after that, simplification and cancellation of the term will provide you only this term. Now I would like to consider the remaining term. As you can see in this term, the partial derivative of pressure is multiplied with the volume of that element, and since the volume cannot be zero, therefore this term partial p over partial x should be zero. So it means that the change in that pressure in that direction is zero, so pressure will remain same. So this also confirms one of the important Pascal's law, that states that pressure at a point in a static fluid is same in all directions. Subsequently, apply the summation of forces in the y direction, and once you have that, the equation for the change in pressure in that particular direction will include the weight of that element also. So after simplification, the following equation is obtained, and again in that equation the volume cannot be zero, so this implies that this term partial p over partial y should be zero, and this is my equation which is required, that the hydrostatic equation of pressure. Subsequently, the equation can be written in this total differential form, because dependence is only in one direction, and for incompressible fluids our density is constant, the fluid density is constant. So performing integration between two reference points P1 and P2, corresponding heights are y1 and y2, so it will provide you this equation, which is a hydrostatic equation for determining the pressure. And important note here is that P2 is always higher than P1. Now further, for atmospheric pressure, for example, atmospheric pressure P0, this equation can be simplified for determining the pressure at a point within the container to this form: P0 plus rho g and h, where h is the height of the point where you want to calculate the pressure.